Hi guys, I'm putting together this video for the people who might have been late to the live lesson or who might not have made it for whatever reason, the technology and such. So in this, I'm just going to briefly go through the remainder of the questions from exercise 15.1, which I covered the first batch in the first heat transfer video. So if you were here for the live lesson, you can feel free to skip on to the relevant question at whatever point we left off, because I think it'll be unlikely to get through the whole shebang. So just if you're already here for the explanation of one of the previous parts, please feel free to skip on. Okay, so in this video, very briefly, before we get started on the questions, I'm just going to clarify the two kind of situations that could be happening when in these kind of questions that we're looking at today. So far, we've just been looking at situations where something has gained heat and that's caused the temperature to go up, for there to be a positive change in the temperature. This can obviously go in the other direction, where something loses heat and the temperature goes down. So we have to be aware of the two possible situations. I'm going to come back to this in a moment, but the other two things I want to talk about briefly are we're going to start using subscripts. Now, when I say subscripts, here's an example of the equation that we'll be using here. The energy transfer is equal to the mass times the specific heat capacity of whatever thing you're talking about times the change in temperature. But as these get more complicated, you could be dealing with more than one thing. You could have a calorimeter, one of those flasks, and some water in the calorimeter, and maybe a metal block. It can get kind of complex, and it can get very easy to get mixed up. So what we're going to do is we're going to start using subscripts when necessary to indicate which thing we're corresponding to. So for example, if I had a calorimeter of water, I'm going to label that as the calorimeter, and that is the water. When I say subscripts, it's just after each of the parts of the equation, just write underneath it in small letters. Let's say we're talking about the water. The heat energy needed to increase the water temperature is just a little w here to indicate that's the energy for the water, and a little w here to indicate the mass of the water, heat capacity of the water, and the change in temperature of the water. So as I say, it'll become clear why we need to do this when we tackle a couple of the tougher ones, but just a little subscript to indicate which part of the system you're talking about. And finally, when I say system, this would be an example of a system where you've got water, a calorimeter, and maybe you might drop a block of metal into it or something. Now, all the heat that is transferred within this system, for the leaving cert, you don't have to worry about heat escaping into the environment. You don't have to worry about any temperature change that doesn't match what you'd expect. Sorry, I hesitated there for a moment. What I mean is you just have to account for the ideal situation. You don't have to worry about any heat losses. So in that situation, whatever heat is lost by one part of the system must be gained elsewhere, and vice versa. So if something loses heat, it will be gained by another part of the system or parts. So overall, though, the net effect is that you won't lose heat. You might be transferred from one place to another and cause temperatures to go up and down, but the amount of heat in the system will remain the same. Okay, before we crack on to the questions, I'm just going to go back to this these two kind of situations you could be dealing with. So this one indicates when the heat is gained, when the temperature goes up, so heat gain, and this one here indicates heat loss. Now, sometimes you won't know the final temperature. That's sometimes some of the more tricky questions, and they're asking you to find what it is. In that case, what we can often say is we say, right, let's have theta, that symbol, be the final temperature. And then to kind of piece together what happens next, let's say, I'm just going to have, hope you can see that's just the bottom of your screen. Let's say that this is kind of the base. Let's say that this is 0 degrees Kelvin. It's not okay. And let's say the first situation, we're going to talk about heat gain. Let's say that's the temperature at the start. And if this is 0 Kelvin, it'll have obviously gone up. So let's say that's the end temperature, which if you remember we're labeling as theta. And over here, we're going to do the other situation in a moment with the start and the end temperature being lower. Okay, in fact, I'm going to use different colors to illustrate that. Okay, so for the first one, the ones we've been doing so far, it's always been about finding the change in temperature or finding the energy transfer caused by the change in temperature that this has gained. So if we want to figure out the delta theta, so if we're going to find out how much the temperature has changed, it's going to be this bit here, the difference between the start and the end point. So looking for that amount. So to get that, we just take the end and take away the starting temperature. So it's going to be theta minus whatever your starting temperature was. And that was the same for all of the examples we've done so far. In situations where you have to look at how much heat was lost, this time you're looking for the difference between the start and the end again. But slightly different, you're going to take the start and then you're going to subtract whatever the final temperature was, otherwise known as theta. So these are the two possibilities we could be doing. So going back up here, the delta theta here is the change in temperature. A little arrow indicates that it's increased, and here it indicates that it's decreased. Just to kind of bring everything back together. Let's get rid of all this remote. The important bit is for heat gain, it's going to be your final minus your start. And for heat loss, it's going to be your starting temperature minus whatever the final temperature is. So that's kind of the take home from that. Okay, with that in mind, let's get cracking. What I'm going to do is start with question 8. Now, if you were here for part or all of the live lesson, you can safely ignore the earlier bits and go to the bit that you didn't get to. So I'm going to put the question number up at the top so you can see which one we're on. You can just skip until you see that change to a 9, 10, 11, or wherever point we stop the lesson at. Okay, so question 8. I hope you have them in front of you. It's going to make this a lot easier. It's on page 162 of your textbook. If you need to pause the video and fetch them, that's cool. Okay, so question 8. 4,000 joules of heat energy are added to 400 grams of water at 20 degrees Celsius. What's the resulting temperature of the water? Okay, first off, to throw you a curveball here, they give you the mass in grams, which is no good. We want it in kilos. This formula only works the kilos. So let's change 400 grams to kilos, 0.4 kg. So we have our mass. Now, I skipped a step here, really, haven't I? Because what do we always do? Oops. What do we always do in these kind of questions? You write the equation in. Write the equation that you're going to use, because you just get points even for just pointing it out. So here we're going to use the equation of the energy transferred is the mass times the specific heat capacity times the change in temperature. Now we're only dealing with one thing, so I don't need to add any subscripts here, which makes our life a little bit handier. Okay, so what do we know? We have the mass is 0.4 kg. We know the heat capacity of water is 4,180 joules per kilogram per Kelvin. And the problem is we don't know what the change in temperature is. That's what we're trying to find out. So let's take our equation. Q is equal to MC times the change in temperature, and rearrange it. Now remember, even though these are two symbols, this is the one thing. This is the temperature difference. So we're going to treat that as a unit, and that's what we're looking for. So let's get that on its own by bringing these across. So if we divide both sides of the equation by mass times the specific heat capacity, we have Q over MC gives us our change in temperature. And now it's just a matter of plugging in the numbers and checking it makes sense. So for energy, we were told it was 4,000 joules. The mass of water is 0.4 kg. And the heat capacity of water, oops, sorry, I've gone off the screen there a little bit. The heat capacity of water is 4,180 joules per kilo per Kelvin. So, times them out. 4,000 divided by 0.4, it's going to make the number go up. We're going to divide that by 4180. Standard answer is 2.39 recurring. Don't forget our units. So let's have a quick check of the units here. Joules is going to be divided by joules, so that cancels out. Kilogram times kilogram to the minus 1 cancels out, leaving us with just 4,000 divided by Kelvin to the minus 1, which is like saying 4,000 multiplying by Kelvin. So, the numbers, the final answer, the numerical answer, 2.39 multiplied by Kelvin. So our final answer here is 2.39 Kelvin, and that's been the increase in temperature. So we're almost there. The last step then is, if it started off at 20 degrees Celsius, and it's gone up by 2.39 Kelvin. Now remember that a Kelvin and Celsius degree is the same. Their starting points are different, but the difference between 10 degrees and 11 degrees Celsius is the same as the difference between 10 Kelvin and 11 Kelvin. Each one unit is the same. So our final answer is 20 degrees Celsius plus, we can convert this into Celsius if we like, 2.39 Celsius. So our final answer is 22.39 We'll keep the precision, degrees Celsius. So, oops. Just scroll right there for a minute. Boom. And now my computer's gone to sleep. Okay, let's look at question 9. So I'll get rid of all this. Okay. Yeah, that dotted line was just to show what was in camera and what wasn't. So let's go on to number 9. Now this is the first time they throw a couple of curveballs at you. So I'm going to read the question first. If 40,000 joules of heat energy is supplied separately to both 2 kilos of copper at 0 degrees Celsius and 2 kilograms of aluminium at 20 degrees Celsius, which reaches the higher temperature? Okay, first off, if this was even, if they both started off at the same temperature, you could just look at their specific heat capacity. So for copper, that heat capacity is 390 joules per kilogram per Kelvin. Whereas for aluminium, it was 910 joules per kilogram per Kelvin. So if this was a fair test and both blocks of metal started off at the same temperature, you'd be easy to see that for any given amount of energy, the copper will increase its temperature much more easily than the aluminium. Because remember, what this number tells us is the amount of joules of energy you need to raise a kilogram of this material by 1 degree. So with the same amount of energy, you can cause much more of an increase in the temperature of copper than aluminium. But they haven't given us an level playing field. That would be far too easy. If that was the case, we could just say, right, straight off the bat, copper is going to increase by the most because it's got the lower specific heat capacity. But they haven't made our lives that easy. They're going to try and make it more challenging. So what I'm going to do for this one, I'm going to just divide my page/screen into a giant T thing, because we're looking for copper versus aluminium. We don't have to use subscripts really yet. We could do, but we don't. This isn't a linked system. These are two separate occurrences. So let's do the copper over here, aluminium over here. So first off, our equation is Q. It's equal to mass. So the energy is equal to mass times the specific heat capacity times the change in temperature. And it's the same over here. Okay, so let's look at what we're given. We're told that Q is equal to 40,000 joules, I should say. And that's going to be the same for both, because these are two separate parts. They're both given 40,000 joules. The mass of each one is the same at 2 kilos. The only difference is their starting temperatures, which we'll come to in a moment, and also their heat capacity. So the heat capacity of copper, you're probably getting familiar with it by now, we've done so many times, is 390 joules per kilogram per Kelvin. And for aluminium, it's 910 joules per kilogram per Kelvin. It's just a matter of rearrange your equation again. So we had Q is equal to MC times delta theta. Q is equal to MC times delta theta. This time we're looking for the change in temperature on its own, just like before. So let's bring these MCs across, like transferring wrappers. So the energy transfer divided by the mass times the specific heat capacity will give us the resulting temperature difference, and that's going to be the same over here. I'm being very pedantic and writing at every step just so you don't, I don't think I've plucked it out of thin air. So let's plug in our numbers. We have 40,000 joules divided by the mass of 2 kgs times the 390. You can't see that because it's gone off the screen a little bit. 390 joules per kilogram per Kelvin will give us our change in temperature, our almost final answer. And here, 40,000 divided by 2 kilos times 910 joules per kilogram per Kelvin will also give us our change in temperature for the aluminium. Okay, now I had this done before just to save time. Unfortunately, I misplaced it. So let's just do the two separately. 40,000 divided by 2 kilos divided by 390. So for the copper, I got a temperature increase of 51.28 Kelvin. Whereas for the aluminium, I got a difference of 21.97 per Kelvin. Now the good news is we're most of the way there, but which would be a little bit tricky here. Remember that what we've calculated is the change in temperature. We haven't calculated the temperature, we've calculated the change in temperature. So because they said that the copper starts off at 0, so if it started off at 0 degrees Celsius and increased by 51.28, we can say this is degrees Celsius as well, because remember the same unit. We've got a final temperature for the copper of 51.28. Whereas the aluminium, they were trying to be a bit sneaky. It increased by 21.97, but it was already at 20 degrees. So let's add that 20 degrees Celsius on. So its final temperature was 41.97, or 42 degrees Celsius. So here the copper was the hotter of the two. All right, let's keep cracking on. Remember, if you have any questions about any of this, always by the chat or email, or you can bring them up in a live lesson as we go. All right, so let's do question 10. All right, starts to get a little bit more tricky again. Now this time we're going to have to start involving the subscripts. So a copper calorimeter of mass 80 grams contains 120 centimeters cubed of water. Assuming no heat loss to the surroundings, how much heat energy is needed to raise its temperature from 18 to 60 degrees? Okay, so let's just sketch out what's happening here. We've got a calorimeter of water. I'm going to say that this is the calorimeter. Remember, it's a physical thing, so it's made of copper, the calorimeter. And that's going to take some of the heat, and the rest is going to go into the water itself. It's going to have that W for water. Oops. There you go. Okay, so they've thrown a few curveballs out in this question, which I'd rather they had only done one at a time. So just addressing the first one, they've given the volume of water as being 120 centimeters cubed. And they also say that the density of water is 1 gram per centimeter cubed. So if we want to find out the mass, now we haven't really talked about, well, depending on where you are, we haven't really talked about mass and density yet, but really it's just a sneaky way of saying that the mass here is 120 by 1 is 120 grams, that's all. So we have 120 grams of water. That was the first curveball. Okay, so we're going to have to start using some subscripts. And let's think about what's happening. What they're doing here is they're adding a... oh no, they're not adding anything. They just have the copper calorimeter and they're heating it up. Okay. So some of the heat's going to go into the calorimeter, some's going to go into the water. Why didn't I just leave that as it was, but whatever. Okay, so the total energy needed to bring these up to 60 degrees. That's what they want to find out here. So the total energy needed to bring the water and the calorimeter up. The total energy needed here is equal to the energy needed to heat the water plus the energy needed to heat the calorimeter. Okay, so the final Q therefore equal the energy for the water requires is its mass. And let's start using those prefixes. So the mass of the water times the heat capacity of the water times the change in temperature. Again, little w of the water. So it's that energy plus the energy required for the calorimeter too. So let's have that as MC. Why didn't I do this before? So I'm going to use C for calorimeter. Okay. Now let's think about what we know. We know that the mass of water is equal to 120 grams, which is the same as saying 0.12 kg. So the mass of water, that is. We know the heat capacity of water is the same as, again, it's 4180 joules per kilogram per Kelvin. We know the change in temperature, if they're starting off at 18 and they want to go to 60, that change in temperature is 42 degrees Celsius or 42 Kelvin, both the same thing. And for the calorimeter, the mass of the calorimeter, let's be a little bit sneaky here, 80 grams again, they're being a bit sneaky. So 80 grams, we don't like grams, we like kilos, is 0.08 kg. The heat capacity of copper is still the same at 390 joules per kilogram per Kelvin. I know the board markers aren't that neat on this. The unit's a little bit smudged there. The change in temperature is the same change in temperature as that 42 Kelvin. Okay, so the total energy here, let's do this one first, is 0.12. Now if it's okay, just because I'm running out of space, I might leave, no, let's not leave the units. Keep the units in. So 0.12 kg times specific capacity of water, 4180 joules per kilogram per Kelvin, times the temperature difference of 42 Kelvin. Okay, yeah, I'm going to leave out the units, but just to show you what happens with the units, remember that we're expecting this to work out as an energy reading, as joules. So let's see if it does. Kilograms by kilograms to the minus 1, they're going to cancel each other out. Kelvin to the minus 1 times Kelvin is going to cancel out, leaving us with just joules. So our unit will make sense, but just so we don't run out of room, if it's okay by everyone, I'm going to just leave them out for now, just put in the numbers. So the mass is 0.12. The heat capacity of the water is 4180. That's kilograms to joules per kilogram per Kelvin, times 42. Plus, and over here we have 0.08 times the heat capacity of the copper, which is 390 joules per kilogram per Kelvin, times the temperature difference of 42. And I've cheated a little here, I've done this one earlier, so I can make sure my number makes sense. So for water, I got 21067.2 joules. And for the calorimeter, 1310.4 joules. And that gave me a total of 22377.2 joules. So just to kind of recap what we are doing here, this was the energy needed to bring the water up to 60 degrees, and this was the energy needed to bring the copper up to 60 degrees. You notice the massive difference in the number. 21,000 joules to bring that water up, only 1,300 odd to bring the copper up, because the copper heats up much more easily than water. Sorry, beg your pardon, ignore that heats up. The copper raises its temperature much more readily than the water did. Okay, let's keep cracking on. Take a break at any point. By the way, don't, you can go get yourself a cup of tea or coffee, whatever floats your boat, depending on the time of day. But I'm going to keep cracking on. So we're on to number 11, which you should now be able to see. Okay, so they have a kilowatt of electric heater supplies heat to 5 kilograms of water and raises its temperature from 10 to 100 degrees Celsius, assuming no heat lost in the surroundings. How long does this take? Alright, so this is a much more straightforward one. The only tricky part here is the kilowatt thing, which I'll come to in a minute. So what's our measure of how quickly energy can be transferred? So if you look at your kettle, it will have a certain watt reading telling you how quickly it will boil. But let's deal with that after. First off, let's figure out the energy needed to heat this thing up. So what have they got? 5 kilograms of water. So let's start with figuring out how much energy is required to heat that. So it's mass times heat capacity times the change in temperature that they need, which is, they say the mass is 5 kilos. The heat capacity of water is 4180 joules per kilogram per Kelvin. And the temperature difference here to go from 10 to 100 is 90 degrees Celsius, which is the same as saying 90 Kelvin. So it's, oh actually, haven't I done this already as well? Okay, so I got 1881000 joules as my answer. That's the energy needed to bring 5 kilos of water up from 10 to 90 degrees. And just checking the units again, kilogram cancels with kilo, Kelvin to the minus 1 cancels with Kelvin to the minus 1, leaving us with just the joules. Okay, so the final step then is, let's go back to this kilowatt kettle thing. So 1 watt is equal to 1 joule per second. That means that if you have something that has a power of 1 watt, it can give 1 joule every second. And a kilowatt is 1,000 watts. So this is telling us that this kettle can transfer, I presume it's a kettle, 1,000 joules per second. So if we want to see how long it takes to transfer this, 1881000, we just 1881000 joules divided by the speed, the power, the rate of transfer, which is 1000 joules second to the minus 1. So boom, boom, joules cancels out, and we're dividing 1881 by seconds to the minus 1, which is the same as saying times seconds. So it's, sorry, it went off the screen. 1,881 seconds to boil to bring that kettle of water up. All right, you're still with me, and that this is still recording. I think it is. Actually, whacking it. just, sorry, uh-oh. Close this. Sorry guys, I accidentally took a screen grab and had to sort it out. Alright, so we're almost there. 12. So for this one, 30 grams of water at 100 degrees Celsius are added to 100 grams of water at 20. If there's no heat loss to the surroundings, what is the resulting temperature of the mixture? Okay, now if you're not fresh, pause the video, get fresh. I don't know what that means in today's slang, but get yourself a drink of water, a cup of tea or something, and come back, because it's going to get demanding for these last two questions. I might follow my own advice in the moment to do the same. Okay, so question 12. 30 grams of water at 100 degrees Celsius are added to 100 grams of water at 20. So let's just picture what they have. You've got 100 grams of kind of coldish water at room temperature, and you're pouring in from something else hot water, but not very much of it. 30 grams of hot water. So this is the hot, this is the cold. Okay, we're going to see what the final temperature is of the whole mixture. Now, whatever heat is lost by the hot water will be gained by the cold water. So the heat lost by the hot water will be equal to the heat gained by the cold. Okay, so let's figure out what that heat is. Now, they're looking for the final temperature. So let's see. Let's go with the heat here. It's equal to the mass times the heat capacity times the change in temperature. And for the first time, we're going to have to start really being serious about these subscripts. So the heat lost, and there's a little arrow down to indicate that's the heat lost, is equal to the heat gained on this side, which is the mass of this water, times the heat capacity, times the temperature difference going up. Okay, now if you remember, we said that we're going to let theta be our final temperature. Okay, so let's deal with this side first, for the heat lost. Well, the hot water, how much of it did we have? We had 30 grams of hot water, which is the same as saying 0.03 kilograms of the water times the heat capacity, 4180 joules per kilogram per Kelvin. Just writing it underneath so we can fit this in. Times the temperature difference. Now, we don't know what the temperature difference is, but if you remember, if you lose heat, the temperature difference is the starting temperature, which for this hot water is 20 degrees Celsius, minus the starting temperature, minus the final temperature. Okay, that's this side, that's the heat lost. And that's going to be equal to the heat gained by the cold water. So that's, how much did we have? We had 100 grams, so 0.1 kg. The heat capacity of water is still 4180. Do you know what? Let me just do this a bit neater. For this one, I'm going to leave off units, okay? Just to make our lives a little easier for this one. So we have 0.03 times 4180 times 20 minus theta is equal to the heat gained to the other side is 0.1 kg times the heat capacity of the water, 4180, times, and this time the temperature difference for the heat gained is the final temperature minus the starting. So that's like saying theta, the final temperature which we don't know, minus, and that water started off at 20. Oops. You've probably been screaming at the screen that this should have been 100, shouldn't it? The starting temperature of the hot water was 100 degrees, not 20. My bad, sorry guys. Okay, I know that looks very messy and complicated. The good news is we can cancel off some of it. The heat capacity of water is equal to the heat capacity of water. So let's get rid of that. That leaves us with 0.03, and I'm going to put the units back in again. We've got a bit of room now. Times the temperature difference on this side is equal to 0.1 times the temperature difference on this side. Now really what we've got here is a little bit of algebra. So what we do, let's bring this fella over here first. Now, by the way, there's many different ways you can figure this out at the end, so if your way is more elegant than mine, you go for it, you do you. But what I'm going to do is I'm going to get rid of this 0.1, I'm going to bring it across. So I'm going to say 0.03 times 100 minus theta. I'm going to ignore units again for a moment, if that's right. Divided by 0.1. Actually, I won't divide them. Let's put the units back in. 0.03 kg divided by 0.1 kg. Cancels. Is equal to theta minus 20. So that's like saying if you divide 0.03 by 0.1, you get 0.3. Check it with your calculator to make sure I'm not making it up. So 0.3 times 100 minus theta is equal to theta minus 20. So we're almost there. So what I'm going to do is I'm just going to bring this line up here, get rid of some of this mess. Remember, you can always pause the video if you want to check my sequence of errors here. But let's go back up here. We have 0.3 times 100 minus theta is equal to theta minus 20. Just multiply it out. 0.3 by 100 is 30 minus 0.3 theta is equal to theta minus 20. All right, let's bring the numbers to one side. Minus 20, bring it across, so add 20 to both sides. That gives me 50. Bring this fella across is equal to our original theta that was already this side, plus, because this was a minus, 0.3 theta. So what we have now is 50 is equal to is equal to 1.3 theta. And remembering that this is Kelvin, I should already have done the units. I might redo that in a second. So 50 divided by 1.3 is equal to theta. Theta therefore works out as being 38, I did this earlier, 38.46 Kelvin, or 38.46 degrees. So that's the final temperature, and I think that's what they were looking for. Okay. Before we kind of leave this question, I just want to show you why I kind of skipped a step there, guys, but why the units work out as being Kelvin. So, going back a moment, I know this has been a very long one. Let's go back to where we had 0.3 times 100 minus theta. Remember that theta is minus theta temperature, and that's Kelvin. It's just that we left out the units earlier on, that's all. All right, so the final answer, 0.1 times theta Kelvin minus 20 Kelvin. It's just because of the amount of room we've got to work with here. So the final answer did work out as being Kelvin. So hopefully you're happy enough with that. Right, the last one is pretty tricky. And I'm tired, so I'm probably going to make a load of mistakes myself. But let's give it a whirl. Okay, so this time we're definitely going to need subscripts. It's a messy one. 120 grams of copper at 100 degrees Celsius is added to 80 grams of water in a 60 gram copper calorimeter at 20 degrees Celsius. If there's no heat lost to the surroundings, find the final temperature of the system. Okay, let's just put number 13 up for anyone who's skipping past me waffling to the relevant bits. Okay, let's deal with their traps first. But first I'm going to sketch out what's happening. So you have a calorimeter. So I'm going to label cal for calorimeter. It contains some water, which I'm going to label W for water. And what they do is they drop a block of copper into it, a hot block of copper, which for this one I'm going to label this as just C. If that's okay with everyone, I'm going to go with C for the copper, W for the water, and cal for the calorimeter. So what's going to happen here? They've heated the block of copper up, and it's going to warm. That heat is going to be transferred and even out the temperature of the whole system. So really what we're looking at here is that the heat lost by the copper, lost by the block of copper, that will be divvied up. Some will heat up the water, some will heat up the calorimeter. So that means that the heat lost by the calorimeter is equal to the heat gained by the calorimeter plus the heat gained by the water. Okay, so just to recap, whatever heat this block of copper loses, it'll be transferred either into the water or into the calorimeter, and whatever heat is lost will be given into these. Okay, now again, we're looking for the final temperature. All right, that's a little tricky. So what we're going to do here is we're going to say, let theta be the final temperature. Okay. So for this one, I'm definitely going to leave out units if that's right to the end, guys, just so that this actually fits on. So first off, let's figure out the heat lost by the copper. So the heat lost by the copper, the big block of copper, which is 120 grams, so its mass is 0.12 kg, no, let's leave out the units. 0.12 times the heat capacity of the copper, which is 390, times the temperature difference. Now we don't know what the temperature difference is, but if you remember, it's gone down, so therefore it's going to be times its starting temperature minus theta. So we know that its starting temperature is 100 minus, and I'm just going to put theta in a different color so we can keep track of it, because my zeros and thetas look a little bit similar. So the heat lost by the copper is equal to the heat gained by the calorimeter. Okay, so what do we know about the calorimeter? The calorimeter is 60 grams, so that's 0.06 kilos. It's also made of copper, so that's times 390. And this time it would have gained heat. Sorry, it would have gained heat, so its temperature is going to be theta minus its starting temperature, which was 20. Okay, so that's the heat gained by the calorimeter is its mass times the heat capacity times the temperature difference. And if you're wondering why it's 100 minus theta or theta minus 120, check back to the start of the video. It's because this lost heat and this gained heat. So the heat gained by the calorimeter plus whatever heat is gained by the water. So same kind of process here. We have 80 grams of water, so 0.08. The heat capacity of water is times 4180. And the temperature difference again is theta minus 20. Definitely need to get a bit more room on this yoke. Okay, so we're now at a point where it's quite algebraic. So I think the easiest way here is, first off, let's handle this side. Let's multiply 0.12 by 390. And I cheated a little, I did this earlier just to make sure. And I got 46.8. And again, we're going to leave out units to the end. Times 100 minus theta is equal. And here I got 23.4 multiplied by theta minus 20 plus 334.4 times theta minus 20. And already the numbers are making sense that this requires more heat to get the water up. Okay. What did I do here? Okay, what I'm going to do next is I'm going to bring this 46 across. So on this side I'm going to have 100 minus theta is equal to, on this side, actually, do you know what? Let me just do something else here real quick. If you notice, 23.4 and 334.4, they're both multiplied by theta minus 20. So just like in algebra, if you imagine that was like an x or a y, you can add these fellas together. So let's do that. So let's say 46.8 times 100 minus theta, it's very wrong color, is equal to, on this side, 23.4 plus 334.4 is 357.4 multiplied by theta minus 20. Okay, now I know that looks a bit messy, but we're almost there. So next, I'm going to bring this 46.8 across. Now, by the way, you may have done this a different way with the algebra. That's absolutely fine. All roads will lead to Rome here, as long as you're careful. I say that before making a mistake. Probably. So 100 minus theta on this side is equal to this side divided by 46.8. 357.4 times... Sorry guys, I accidentally pressed this yoke off. What I've done is just brought that fraction up. It's on the final hurdle as well, and I'll talk about the last kind of couple of seconds. Closing, snatching defeat from the jaws of victory. Okay, so we have 100 minus theta is equal to 357.4 times theta minus 20 divided by 46.8. So first off, let's just divide this in, and you get 100 minus theta still on this side. I've stopped doing theta in a different colour because it's now clear that that's theta because it's not as messy. Is equal to 7.636 and change on the calculator, multiplied by theta minus 20. Then it's just a matter of multiplying it out. So 100 minus theta is equal to 7.636 theta minus 152.735. Okay. Let's bring this number across, giving me 252.735. 100 plus this, I'll bring this across, add both sides, is equal to, on this side, we had 7.636 theta. Let's bring this theta across, which gives us 7.636 theta plus theta. And you know what? I am just going to underline that so you can see the thetas. So that gives us 252.735 is equal to, well, 7.6 theta plus theta is 8.636 theta. And our final answer then, if we want to find what theta is, let's divide both sides by this. So 252.735 divided by 8.636. It's going to give us our theta, which is, I got 29 degrees. I'm going to be careful not to turn this off this time. 29.26 degrees Celsius. Oi, right, bit of a long-winded one, and kind of tricky, I think, because I threw you some grams instead of kilos. But please work through it. Make sure that your answer agrees with mine. To be honest with you, that started off clear enough and then ended up not being very clear. But it's been a long day, so I might even tackle that one again at some point in the future. All right, guys, we're going to leave it there for today.